welcome to Pythagoras 1. We'll get going. Here we go with Pythagoras 1 and welcome back. Okay, that was Right Said Fred. Now, that song Deeply Dippy is all about I don't know what it's all about. But the reason I chose it is because it's right and right for right angle. Okay, right for right angle. That's the reason I chose that this morning. Right for right angle. Right said Fred with the singers. All right. Okay, so let's get going on this one. Okay. So we've got a right angle there. Okay. Oh, and deeply dippy about the curves we got. So if we were talking about curves here, let's just a side track here. Okay, so just to get us going, curves, right said Fred. Let's have a look at that. All right, just a side path. So I want you to think about the curve of that one. What would the name of that graph be? What would the name of that graph be? Okay, so that graph would be y equals x squared. Okay, so that's just a little bit of a sidetrack because of the tune we've got this morning. Right said Fred, deeply dippy. Okay, and right for right angle. So let's make a start this morning on right angle triangles. Okay, and let's have a look at this Pythagoras business. So where does Pythagoras come from? Why is he the guy that's been credited with it and all that kind of stuff? And what is it? Right. So first of all, Pythagoras, he was Greek, but actually, you know what? He just kind of got the idea of this theory from other people. So it was a little bit of a cheat, really. He got credited with it, the Greek guy, but actually the Egyptians found this out many years before Pythagoras. But Pythagoras is famous for spotting this pattern. Pythagoras was a decent mathematician, though, and he was found lots and lots of other things out. And something to bear in mind with maths is that the Greeks were really, really good at maths years and years ago, and lots of theories are down to the Greeks originally. So, yeah, I'll give him that. Okay, well done to Pythagoras for getting that. Okay, so let's go back to this. Where's it come from then? Okay, so we've got the shape of a right angle triangle. Okay, so on this right angle triangle, okay, just like trigonometry, okay, we can use this to find sides. But actually, the theory has got nothing to do with sides. Well, it has and it hasn't. It's to do with area. It's to do with area. But one thing we could do a little bit of revision here from trigonometry, okay, is it is useful to know what this side is and why it's called a side, a name, and things like that. So, those of you maths fans out there, I'm just going to give you a second, okay? And good morning to Miss Davis, by the way. Well done for joining us this morning, okay? And Mrs. Howard as well. Well done. Good morning to those people. So, if you can type in what do you think that side is called, that would be great. Okay, so that's called a hypotenuse. A hypotenuse. And the reason why that's a hypotenuse is because that is the biggest side. Okay? Hypotenuse. Well done, Lydia. Hypotenuse. Brilliant. So we've got a connection between these three sides. We've already looked at trigonometry. Normally we go Pythagoras first, but we've done it in a different order. They're only related because of right angle triangles. Other than that, the connections are not quite related. But often you can get a Pythagoras question mixed in with the trigonometry because they're both dealing with right angle triangles. Okay, so what we want to do then is have a look at some areas, okay, so that we can see what that connection is. So we're going to use these sides, and what I'm going to do is I'm going to measure this side and I'm going to make a square attached to that side, okay. So this is the side, it's one of the smaller ones first of all, and we're going to make a square from that side. So measuring that to be 3 centimeters, okay, and I've made a square, so that's going to be 3 centimeters. All right, so next question, I want the area, because actually Pythagoras, although it's and its sides, it's really, the link is to do with area. So I want the area of that square, please. Answers to be typed in. And 3, 2, 1. Have we got any answers coming through? The area of a square 3 by 3. Okay, that's right. It is 9 centimeters. Brilliant, because area is length times length. Well, if the lengths are both the same here, it's 3 times 3 equals 9. Brilliant. So, in terms of the units, we mustn't forget that it's centimeters with a little 2, and that's measuring how many squares that takes up. Now, if I was to like draw squares on here, just a little bit of a sideline here, okay, that's not quite a little square. 1 centimeter squared, we know that it's 3 along, 3 across, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9 squares altogether. Okay, now I haven't drawn that in the right place, but I'm going to do the same for this one. Okay, so this is measuring 4 by 4. So I'm going to draw a square added to the side of that. So that's 4 centimeters by 4 centimeters. I haven't left much room there, but still fit in. Okay, so what's the area of this square going to be? So I'll just write down at the side here. The area of the first one's going to be 3 times 3 equals 9 cm squared. Area of the second one, we'll call that area of A, area B, area B. Okay, so it's going to be 4 times 4. Any offers for answers there? $16, brilliant. Okay, well done, Lydia. Again, good answer. 16 centimeters squared. So that gives us 9 and 16. Now, the interesting thing is we might as well do it for the hypotenuse as well while we're doing it for those three. So let's just have a little bit of a measure there. So 5 centimeters, yep, that's great. So let's just make a square here. 5 centimeters. I'm kind of using the measurements of the ruler to get the right angle, the scale to get the right angles in the right place. Okay, so there's a square there. 5 centimeters, 5 centimeters. Okay, so I need the area of this third square now. We'll call that C. So we've got 5 times 5, and that's going to give us 20. Oh, well done, Alfie, for the last one there. Brilliant. Got 16, so we just filled it in. I couldn't help myself. 5 5s are 25 centimeters squared. Now, this is the issue here. So we've got 2 little squares and 1 big square. What is the connection between these two here? These two, well, all three actually. What do you notice? Okay, so 9 and 16 makes 25. Brilliant. So what we can do is if we add, though, the connection is if we add the two smaller areas, it makes the third area. And that is what Pythagoras found. The areas of the two small squares from a triangle make the area of the third square. Okay, so that's brilliant because that we can use this idea of to find any missing squares. So if there's a connection between this, and this square, that means that if I've got two of them, I can find the third. Okay, so brilliant. Now, if I was to cut this out, I'm not going to today, but if I was going to cut this small square out and this medium square out and cut them into 1 centimetre squares and place them, it fit on that area exactly. Right, brilliant. So how are we going to use this this idea? Okay, so going back to the square, the triangle, I'm going to draw another one now. So I'm going to make that. We're not going to draw squares on here, but we are going to find areas. Right. So on this example here, what I need to do is find the distance of that side. So if I measure this one to be 5 and this one to be 12. Now you might be saying, why don't you just measure the third one? And I suppose I could, but actually if we're looking for really big accuracy in terms of engineering and things like that, okay, and sometimes it's not possible to measure that. I suppose that's the roof of a building or something like that, so it might not be possible to find that third side, but we can use it doing Pythagoras. So what we need is the area of the square. I just kind of draw it in a little bit here. I'm not doing it accurately, but just sketch it in. So the area of that square there, okay, let's go over it a little bit. There we go. So that would be 5 times 5, or 5 squared, 25. We've already done that on the other example. And then we can't fit this in at all because of the size, but the area, if we had a square underneath, would be 12 squared, 12 times 12, and that is 144. Okay, now we don't know this, but we do know this area here. Okay, oh, well, that's 5 there. I don't know why I did that, but anyway, the area is 25 and that's 144. So to get the area of this square here, if we were to draw it, would be 144, okay, added to 25. Okay, so the area of this is going to be 169 centimeters squared. So this is the last part for today, is how can I get from the area of that square there to give me one side? And the clue here is that this side and this side of the square are going to be the same. So it's going to be the number times itself. And if you look at this sort of 5 squared here, it's going to be the reverse of that. So I'll give you a second. What function will give me the side given that the area is 169? Okay, so I'll give you a second. Please type your answers in if you can. So I'm looking for the function to get from the area to the actual side. Okay, just waiting for some answers to come through. Okay. Good morning to Alfie Howard while we're waiting. Good to see you on board for this morning. Brilliant. Okay, and it is the square root. That's right. So the opposite function, the reverse function of squaring, is going to be the square root. So if I know that this side here, and let's call it x, and this is x, x times x is going to be 169. To find out what x is, I need the square root, because it's the same number, 169. So I need the square root of 169. So how do I work that out? Okay, calculator job. But actually we could do it without a calculator, but I'll do use a calculator. Square root, there's a square root button there. Square root 169 equals 13 centimetres. Boom, 13 centimetres. Not squared, 13, because that is the size. So, brilliant. So to recap this morning, what have we done? We've looked at the first part of Pythagoras. We've learnt that the areas of the squares of each of the sides of a triangle are connected. The two smaller areas make the big area, okay, or the two areas of the small size equals the area of the hypotenuse, the square of the hypotenuse. Then we've learned how we can use that idea to work out a missing side by finding the area of the two smaller squares, okay, and that makes the area of the hypotenuse squared. And then to find the actual side, we reverse the square idea with a square root. Okay, so that's it for Pythagoras 1. There is going to be more to this, but that will be tomorrow. But this is really just giving us the idea of what the rule actually does. Okay, so we looked at right said Fred, chosen because of the right angle, okay, but actually that particular tune was talking about curves as well. So there's a curve here, okay, y equals x squared. So I'm going to leave you with this little question. Maybe we can answer this tomorrow. We've done the y equals x squared, but what would be the name of this shape? Okay, so our x-axis, our y-axis, okay, so on. Okay, so going back to this shape here, it's y-axis, x-axis. We said this, the name of this shape was y equals x squared. So the question is, what is the name of that shape? So before I will give you the answer to that, y equals, just give you a bit of time to think about it, x squared, and it is negative x squared. And just a sideline track while we're just talking about that is actually it's a reflection in the x-axis for those of you doing higher level. If you're doing intermediate, it's just good enough to learn which is which. And that's it for today, folks.